Polynomials continued. These things start to get harder and harder with more and more theorems until you get to a certain point where you start to realize the structure underlying them, and they start to all pull together. It pulls together in nice theorems like this. What's a polynomial? Well, what's a polynomial? X to the n power, another whole power, all the way down to a number times the power plus a number. So these are just indices for n plus one different numbers, but these are pure powers. Every one of these, how does it factor? What do we learn about factoring polynomials? This is where it starts to pull together and look simpler, hopefully. Factoring was pretty difficult, wasn't it? We're going to make it a little more difficult today, too. But it always factors as the lead coefficient, an, times x minus x1, x minus x2, x minus xn, where x1 through xn are called the zeros of the polynomial. And there's always exactly n of them. So what we found out from before is that every polynomial actually factors like this, where x1 to xn, some of them may repeat, are called the zeros. Of the polynomial. They repeat. You may have one that goes up more than once, and they may be complex. All right, so they aren't all real numbers. So it always breaks down like that. What do we know about any of the complex zeros? If these numbers here, a0 through an, are all real numbers. So if it has real coefficients, we call these numbers that multiply the powers of x coefficients. If all coefficients, a0 through an, all n plus one of them, are real numbers, decimal numbers, not having square root of minus one in them, then what do we know about this factoring? Call this equation 1. Then any of these complex zeros, all of them, come in conjugate pairs. In other words, if one of these zeros, x1 through xn are the zeros, they're just numbers. X is the variable. If one of these is complex, a plus ib, then its conjugate, a minus ib, is also a zero. So they come in pairs, and those pairs multiply into irreducible quadratics. In other words, quadratics that don't factor, just using real numbers. Okay, so this really helps us to figure out how to factor these things. And we did a couple of examples last time. When I said factor, this was one of the homework problems here. I can't see the number up. Factor p of x, a polynomial, is x to the fourth plus x squared, we said. How does that factor? Here's how you do these things. You first pull out the greatest common factor, the largest number that goes into the coefficient. So that's just 1. And the largest power of x you see in all of them. So you pull out the greatest common factor, x squared, and write that as x squared times x squared plus 1. Now, how do you factor the rest? This is actually an irreducible quadratic, meaning b squared minus 4ac is less than 0. Quadratic's a second power polynomial, second power. Irreducible. So this is as far as it factors over at reals. Stop here for real numbers only, for using real numbers only. But it factors further if you use complex numbers. Its fourth power is the highest, so we call it a fourth degree polynomial. That means I can write the lead coefficient times 4 of these. How does it factor overall? You can, on an irreducible quadratic, you can find the zeros by using the quadratic formula. Right? The zeros are what make this equal to 0. So the zeros are x equals minus b plus or minus square root b squared minus 4ac all over 2a by the quadratic formula. Where this is 1x squared plus 0x plus 1. So a is 1, b is 0, and c is 1. And you say that the zeros are minus 0 plus or minus square root 0 squared minus 4 times 1 times 1. All over 2 times 1 is, let's see, square root of minus 4 is 2i, right? Minus 4 is 2i, 2 squared minus 1, and that's over 2, so plus or minus is plus or minus I. So the zeros of this irreducible quadratic are plus or minus I. That means that it factors as its lead coefficient 1 times x minus the first of those, I, times x minus the second one, minus I. I'll call it minus and minus I is plus I. And this is how the whole thing factors. I can leave the 1 out of here now. B, C. This polynomial factors completely as x minus 0, x minus 0. All right, so this is this one. If you say it's its lead coefficient, 1 times x minus 0, x minus 0, x minus I, x plus I, it factors like this. Fourth degree has 4 factors times the lead coefficient. That's this here. That was our example. Does that look familiar? I hope. But that's how these all work. Every polynomial, when you allow complex numbers, factors like this. Lead coefficient, x minus 0, x minus 0, x minus 0, x minus 0. The zeros, remember, are the polynomial, are the numbers x you can plug in to make the whole thing equal. All right, so it factors this far using just real numbers. This doesn't reduce any further with real numbers, but if you allow complex numbers, you can factor it all the way to here. Right. Well, then we did a couple of other examples, and I want to do some more today. And the following graphic note. Note real zeros, not I and minus I here, but 0 and 0. And by the way, you don't usually write it this way, fully factored. I just did that to show you it fits the formula. Usually write it like this, just to be, just for brevity, I guess you'd say, to be succinct. So you write it like this, and you recognize it's this in the formula 1 there. So the real zeros, the numbers, we had the factor theorem that says that if these are the zeros, then the factors are x minus those numbers, right? X minus I. If I is a factor, then x minus, if I is a 0, then x minus I is a factor. If minus I is a 0, then x minus a minus I is a factor. That's how we need to factor it like this. Right? The factor theorem says that's the relationship between the zeros and the factors. Each 0 corresponds to a factor x minus that number. All right, so the real zeros, which would be just 0 and 0 here, of a polynomial p of x. Right? A polynomial is just a function of that form 1. Tell you something about the graph. These are very important if you go on to take higher mathematics, and they expect you to know these. For instance, in calculus, it really helps you a lot to know this algebra. You go to plot in the xy plane, y equals p of x. This is what you get. What is a 0? A 0 is a number that plug into p of x and makes p of x equal to 0. So by its very definition, the x-intercepts are the zeros, the real zeros. So you have an x-intercept if and only if x is a zero, right? Because that makes y equal 0. Zeros are the values of x such that of x 0. That's my definition of x-intercept. Now, what's more is this interesting concept. A zero of odd multiplicity corresponds to a point where the function crosses the x-axis. Think about it, you can see why. We'll mention as we go here. But one of odd even multiplicity corresponds to a point where the polynomial just touches the x-axis and bounces off, goes back where it came from. Came from down, it goes back down. It came from up, it goes. It's a point where the graph bounces off the x-axis. That term loosely, it's not a official mathematical term. Bounces off the x-axis, doesn't cross it. And then also the long-term behavior, or in other books they call it the end behavior, of P of X is that of its leading term. If the leading term goes up on each side, then P of X does. If the leading term goes down on each side, then it goes down. The whole graph goes down on each side because it dominates the other terms for X big positive or very negative. Long-term behavior of P of X is that of its leading term, which you know how to graph it, so you know what it does. Leading term meaning the one of highest power. All the things that are added together, the terms. And every polynomial has a smooth, continuous graph. Can't prove that now, you can prove it in calculus. We haven't defined what continuous means. So continuous, it means it doesn't have any breaks in it, is intuitively what it means, right? If you take a garden hose, it's continuous forward, right? But if you cut it, then it's not continuous. So continuous means it has no breaks in it. And smooth means it doesn't have any corners in it, or worse. So it's one piece with no corners in it. So let's try that. Try applying these to the example we just did. Let's just roughly sketch graph of y equals x to the fourth plus x squared. What does that look like? Oh. Well, we factor it. It factors as x squared times x plus I times x minus I when it's completely factored. And what is tell? The real zeros, and by the way, on the problem sets, when they ask you for the zeros in this section, they only want the real ones. Okay, so on infinity, when they say find the zeros, they only want the real zeros. But on the homework I gave you, they also want you to find the complex ones. So the homework page I handed out last time, let me know if you didn't get it. It's also on D2L now. You can download the homework page. The extra homework that's not on infinity, find all the real and complex zeros. On infinity, just find the real zeros, right? Because those are all you need for graphing, as you can see. All right, so roughly sketch this. We can do step one. What are the x-intercepts? Well, let's say first the zeros are what? Values of x that make this equal to 0. I should say the real zeros are simply x equals 0. It's a 0 multiplicity 2 because you have your x minus 0 times x minus 0 if you multiply it out. So 0 is a 0 of the polynomial, something that makes this equal to 0. Well, multiplicity 2 from the factorization because there's two factors x minus that number. It has multiplicity 2. Right? So what do I know about that? The only x-intercept is that x equals 0. And it bounces off because it's an even multiplicity. So I know to do this. And then furthermore, what's the in? So 1, the only x-intercept is that x equals 0. The graph bounces off by 2 because it's an even multiplicity. And then I have the in behavior here. I could call that 3, but I'm just giving properties of the zeros up here. But I'll call it 3 over here. What's the in behavior? It's that of the dominant term, the highest power term. Behavior of the simple function y equals x to the 4th, just the leading term. All right. So what does y equals x to the 4th look like? We memorized that one. Remember how these work? How powers of x work? You have to memorize this graph. Y equals x is this line that splits the axes, right? Y equals x squared is the basic parabola that you learned in previous algebra. That's parabola like that. We used it to get other parabolas in this class. Y equals x cubed looks like this. They all go through this nice 0.11 here, by the way. And some of them go through, the even ones go through -1, and the odd ones go through -1, -1. All these graphs. Y equals x cubed is steeper than x squared out here and then flatter in here. And then it's an odd function that goes like that through -1, -1. So all the odd powers go through, all of them go through 0, 0. All of them go through 1, 1 when you take powers of x. This is y equals x cubed. And the odd ones also go through -1, -1, and the even ones all go through -1, 1. And so then we can do what's y equals x to the 4th. It's even steeper out here, goes through 1, 1, flatter in here, and then goes through this one because it's even. Here's y equals x to the 4th. Then you do y equals x to the 5th, if I have another color. Y equals x to the 5th is steeper than x to the 4th, and it goes through 1, 1, right? Because 1 to the 5th is 1, right? So it goes through 1, 1, but it's steeper here, flatter here. 5th power, it has to go down through here. So this is what they look like. They get flatter and flatter in here, steeper and steeper out here. The odd ones go up on the right and down on the left. The even ones go up on both sides. That's for powers of x. But you memorize that, so now what does y equals x to the 4th look like in each end? Well, it's up on both sides, right? It's this blue one, up on both ends. So the in behavior of our polynomial, this is going to dominate for large numbers. This one's going to overwhelm this one for its size. If x is positive or negative, it's going to overwhelm this one. So the in behavior of y equals x to the 4th is up on both sides. That's what we've got here. So we draw this steeply rising on the ends. And then we said, well, it only has one x-intercept, it's right here, so it's going to hit the x-axis at the 0, x equals 0. And then it's going to bounce off there. So it's going to look something like this. Looks a lot like a parabola, actually, but because it's got that fourth power, then it's steeper, actually. Well, that's not that flat because it's adding the two together. The point is that it only touches the axis here, it bounces off, and it goes up on both sides. Now, sometimes it can wiggle in between, and we don't know that yet. That's for calculus to figure out. Sometimes it can wiggle in here. This one doesn't. Because what it's doing is it's adding this parabola y equals x squared that looks like this to the steeper function y equals x to the fourth that looks like this. Again, you get something that looks like this, but some of them are complicated. You take x to the fourth plus x to the third. It's harder yet. But it can wiggle around in the middle, but at the ends, it has the behavior of x to the fourth up on both sides. It only has this 1, 0, and it bounces off. So there's a rough graph, y equals x to the fourth plus x squared. And now I hope you brought your calculators. I said to bring them before, and I didn't quite get to them last time. You can try the calculator to sketch. Use calculator. If you don't have one that's graphing, you can still plot a couple of points, right? You can plot, for instance, at x equals 1, it's easy. 1 plus 1 is 2, right? At minus 1. Minus 1 squared plus minus 1 squared is again 2. So it's got this kind of behavior, right? And so you can plot the point 1, 2 and the point minus 1, 2. And you can plot a couple other points and get a pretty good idea what it looks like. Better use calculator to plot points or even make the graph itself. The trick is you use these techniques here to figure out where it's likely to wiggle and what it's likely to look like, and then you try and plot it near there. So I want to plot this one near x equals 0 since it's the only place it comes close to the x-axis. And if I go on my calculator, here's what you can do on your calculator. This will be TI 83 and 84 instructions. They're identical instructions for us. They're almost identical calculators. But this applies to lots of other calculators. I have a TI 89 that works the same way, except you have to push second graph instead of you have to push 2 buttons instead of 1. HP calculators are not too different, right? But these are specific for TI 83 and 84 calculators. Normally, I bring these to class to hand out for people who want to do this, but with COVID, I just don't want to. So hopefully you brought your calculator. If not, try it at home. TI 83 and 84 calculators. Here's how you can graph a function. It's really easy. There's top row of functions. You push y equals, the y equals button in the upper left corner. All right, it's right up here after you turn it on. Y equals brings up a list of a big page like this that on the TI says y1 equals, y2 equals. This allows you to plot multiple functions. So you can enter one function, enter another, and put both graphs on the same page. It's very cool. Y3 equals, you can sketch a whole bunch of them. Modern calculators allow you to do in different colors. You don't have to buy an expensive TI 84, 83. These are way overpriced. Casio and Sharp have calculators that are probably a third of the cost of these and do just as much. It's just they aren't official classroom calculators for your high schools and stuff. So you know, when you do them in high school and college, they may not have you may probably have these because that's what high schools have deals with. And people get started in those in school and then they just carry them into college. So if you have one of these, great. If you don't, it'll work just as well, but the instructions will be slightly different. They make nice, cool, multicolored plots of these things. And what happens is when you push this button, y equals, this comes up on your screen. Y1 equals, y2 equals, y equals, 3 equals. And what you do is you enter the function. For this one, you enter, there's a button that says x tau theta n. And this is for plotting with different kinds of coordinates. X is for xy coordinates. Tau is for parametric coordinates. You get those in calculus. Theta is for polar coordinates. Maybe you've seen those before, but probably not. They're usually trigonometry in the next course after this. And n is another thing. I think it's statistics. I don't remember. But you push this and an x appears on the screen. And then you can push this hat or the caret that's over here on the calculator 4, and it takes x to the 4th power. Right? And now plus on your keypad over on the right, x, and there's an x squared button, or you can put hat 2. They both work. I'll put this button, but the button that says X squared will put a square on there. And then you push enter, and what you've done is you've just entered the function, right? So you push y equals and enter the function, in this case, x to the fourth plus x squared, right? That's one. This is a 1, 2, 3 method. Push y equals and enter the function. Hate these things. That's y equals over here and enter the function. Then you push window, the second one from the right on the top. Window. And that tells you how to plot the plotting, gives you instructions to set up the plotting limits. Right, the window is the plotting limits. And tick marks. So you enter those. Let me put this x to the fourth plus x squared. And you push enter to get rid of that. And you push y equals window. And it will, when you push window, something like this will come up. X min equals x max equals x scale equals y min equals y max equals y scale equals, and then it has x res, which we don't need. But this is the minimum x, maximum x, minimum the distance between tick marks, tick spacing here. If you want 1 unit apart, you put in 1. This is the maximum x, just x to plot, just as you guess. This is the minimum x to plot, and it tells you the plot window size. And then here's the min and max y values. If you don't push this, it'll set to whatever you had it last time, or default if you reset it, I think to -10 to 10 in x and y or something like that. So this is the minimum y to plot, maximum y to plot. And this is important because if you don't put these in, it will maybe miss your whole graph, right? Y scale is the tick spacing in x and y, excuse me. Tick spacing in x up here, tick spacing y here. And it just tells you the plot one. Then the third step is this, push graph, which is over at the right. So y equals enter the function, window enter the plot limits, graph, and that's it. 1, 2, 3. You can plot your function. If you want to plot more than one, then on this step, you just push enter, you push an arrow to go down to the next one, enter a new function. So you can enter one, arrow down, enter another, arrow down. And when you're doing all this, you can use the arrows to move up and down. The arrows are over on the right here. Use arrows to move around as you type in. I don't know if you're going to be able to see this, but I'll just plot this from, let's say mine, it looks here like I better not go too far to the side or it'll go off the top of the screen. I'll just go from x min here. Let's put in -2. And by the way, you have to use the negative, not the subtract, or it'll throw an error. It wants the negative sign down in the corner here, not the subtract button here. Then I'll go up to 2. X scale, let's put the x tick marks 1 unit apart. Y min, let's plot from 0 because we know it doesn't go below the y-axis, right? And let's plot it up to, well, if I put in 2, I'm going to get 2 to the 4th is 16, plus 4 is 20. So I'm going to plot up to 20 because I know when I plot x equals 2, I'm going to get y equals 20. So I'll go -2 to 2, one tick space between each tick mark, 0 to 20, and here I'll put 5 between each tick mark because I don't want to get 21 of them in here from 0 to 20. And now let's try putting those in. So -2 to 2, spacing 1, 0 to 20, spacing 5. And then I'll put, so that's the second step. I'll put y equals, enter the function, window, and enter these plot limits. Then I'll put graph at the right, but it's just 1, 2, 3, left, second to left, and right. Uh-oh, and I've got a typo in here somewhere. Let's see what I did. Syntax error, so let's try again. Y equals. Oh, I pushed square instead of x. All right, let's try that again. X. Must have hit an extra key. Now I got it, I think. Graph. That's strange. It's in some sort of strange mode. Once in a while, your calculator will be like in polar coordinates mode and it won't look right. It should show the XY axis here. This one is doing something strange. Let's see, that's one of my characters in here. Try it again. Graph. There it goes. All right. And so it shows me clearly that now this guess was correct. It looks just about like this. And we'll plot it accurate. And then there's two other buttons, zoom and trace. You can zoom in and out. You can push the trace button and it will mark little points on here and give you approximate coordinates so you can plot carefully on your paper. So I'll leave those out. I'll just do the 1, 2, 3, and you can try the zoom and trace on there to move around. But y equals enter the function, window, enter the plot limits and tick spacing, 3, push graph. Any questions on that? Can you do that to check this? And then on the test, what you can do on the final exam is use these things to figure its general shape and then use the calculator to make it a little more accurate, see how it wiggles in the middle. And calculus will put more teeth into this, tell you more about the wiggles. Then we also have these following comments that we learned last time. You know, how do I know the polynomial doesn't go like this? How do I know that? Anybody? From what we made our comments last time, the proof is calculus again, unfortunately. It's amazing what calculus did for mathematics. It made even these simple algebra things much more understandable. We also know, recall, that p of x, a polynomial of degree n, has at most how many turning points? For that, where it turns from going up to going down or from going down to going up. How many times can it do that? You prove it in calculus, you have to memorize it now. It has at most n minus 1 turning points. So if it's fourth degree, it can't turn more than 1, 2, 3 times. Right? It can't do more than this, right? 1, 2, 3 turning points. So it can't go up and down all those times. But your calculator can help you to figure that out. Sometimes it'll have less, like this one only has 1 turning point. But because it has to go up on both sides, right? It has at most 3 turning points since it's fourth degree. It either looks like this with 1 turning point, or it looks like this with 3 turning points. One or the other. That's it. Right? And it might be something kind of in between where it's 1 turning point and kind of wiggles like that. But so it has at most n minus 1 turning points. Our graph can't have more than 3 turning points, and in fact, it has 1. And we had inflection points. What about inflection points where it switches from bowl shape down to bowl shape up? That's an inflection point. Or it should, so we call this concave down and concave up. And where it changes from bowl down, concave down to bowl shape up, concave up, that's called an inflection point. Also, if it goes from concave up, concave down, bowl shape up to bowl shape down, that's an inflection point. Whenever it changes its concavity from a bowl down to a bowl up or bowl up to a bowl down, it has at most n minus 2 of those. So turning points are where it switches from going down to going up or going up to going down, here and here. And the inflection points are when it switches concavity. That tells you a little more. It doesn't wiggle forever. Fourth degree polynomial has at most 3 turning points and 2 inflection points. Now we can use that to make our graphs more rigorous. And here's some other ones that they have in the homework. How about this one? This is number 10, except this is different numbers than yours, I think. Example number 10. Suppose I take f of x equals minus x to the 4th minus 6x cubed minus 9x squared. 1, find the zeros by factoring. My minus here is minus x to the fourth. I said it, I didn't write it. Minus x, 6x cubed minus 9x squared. Weird how the brain will say one thing and do the other. You ever seen this? They had a show many years ago called The Brain. Anybody ever seen that? It's like a 30, 40-year-old show, but it's incredible what goes on in the brain. They've got these people who had epilepsy. It does severe brain damage. You go into an epileptic seizure and you can't stop. And you bite your tongue off. You'll bash your arms on chairs and break your arms. And so it reduce in the really severe cases. In the really severe cases, to reduce that, they've severed people's brain halves partly. And what that does is the brain halves can't communicate. And so then if you show them with one eye that doesn't control the speech, they know what it is and you can write it with the hand on that side, but they can't say what it is until you show it the other eye, and then they can say what it is and write it with that hand and not the other hand. And sometimes the brain does that even with, my brain halves are partly severed, I think, too. So I'll write one thing and say the anyway, it's very fascinating show if you ever get into the brain. It's amazing. So here's find the zeros by factoring, it says. What are the zeros of this thing? What you do is you can factor out the greatest common factor, the biggest number that goes into -1, -6, and -9. Well, it's just 1, or you factor out -1 if you prefer. I like -1, but you can do 1. The greatest number that goes into 1, 6, and 9 is 1. So pull that, that's all you can pull out. And then times the biggest power of x that goes into all these is x squared. And I factor that out here. -1x squared times x squared gives minus x to the fourth. -1x squared times minus 6x gives minus 6x cubed, right? And -1x squared times times 9, this is plus, sorry, plus 9 gives minus 9x squared. So there it is, pulling out the greatest common factor. We'll say GCF. Pull out the greatest number that goes into these three numbers, the greatest power of x that goes into these three powers of x. Now what do I do from there? So my -1 is minus. How do I factor that? This one I can probably guess what goes in the blanks, right? You can either use the quadratic formula or you can guess what goes in the blanks. If I guess what goes in the blanks, and I know it's going to work actually looking at it, I want blank x plus blank, blank x plus blank. What goes in here is ones. Since the lead coefficient is 1, that's all I put in here. I'm going to put -1 and -1, but then I pull them out and cancel them, so there's no point. And then what goes in here has to have product 9, and since this lead coefficient is 1, only in that case, has to have sum equal 6. So what two numbers sum to 6 and multiply to 9?
3 and 3.
3, yeah. 3 times 3 is 9, and 3 plus 3 is 6. There we go. It factors like that. This factors as minus x squared times x plus 3 squared if we say how it's factored. Now, what are the zeros? We write it out more suggestively like this. This is -1, the lead coefficient, times x minus 0 times x minus 0 times x minus -3, x minus -3 following 1. Equation 1. And these are the zeros. 0, 0, -3, -3. 0 is a zero of multiplicity 2. -3 is a zero of multiplicity 2. So what do I know about this graph of this thing now? These are the x-intercepts, 0 and -3. Are precisely the zeros of the function, right? Does it cross through or does it bounce off? They're even multiplicity 2, right? 2 of these and 2 of these. They bounce off the x-axis because they're even multiplicity 2. What's the in behavior of the graph? Of the lead coefficient, the leading term, minus x to the fourth this time, which looks like what? We take minus x to the fourth, we turn it upside down, right? So now it goes like this. So its in behavior is like down on both sides. our graph may wiggle in the middle. This is the graph of y equals minus x to the fourth as x to the fourth term. That just tells us our graph is going to go down on both sides where this term dominates. This is what we call the dominant term. The highest power term is the dominant term. For x very big positive or very negative, this will overwhelm the size of the other ones. And so it goes like this on the ends. It bounces off the x-axis at 0 and -3. It has, since it's fourth degree, at most 3 turning points and 2 inflection points. So what is it going to look like? Erase this. Well, here's the x-intercept 0. Here's the x-intercept -3. It goes down over here and down over here on the left and right. What can it do? It can only do this. It has to bounce off here. It has to bounce off here. So what happens is somewhere in here, it wiggles around and back like that. And it's a smooth function. You don't put corners or jumps, right? It's a smooth continuous function. So there's no jump, no corners and no jumps. Something like that. Now we don't know exactly, right? It might be that it looks more like this. How far it goes down, we don't know. What you can do to deal with that is you can put in a few values and plot some points, or let the calculator plot the whole function for you between -4 and 1, right? So you use your calculator, plot this area. Plot by calculator, and you should see this behavior, and then you can put some teeth in it. How far does it go down here, kind of thing, right? You might try figuring when you set the plot window, well, when it's at -1.5 with y, and that would tell you about how far down to plot. Any questions on that one? On the final exam, I want you to be able to draw rough sketches. It says it on the homework, but it's hard for them to test you on it. But because it says that, I'm going to put that on the practice test too. I want you to be able to do that. Here's another interesting one. I put this on the practice exam also. Oops. Where's the rest of the problem? There it is. Yeah. Find a possible equation for this graph of going into a polynomial. So if I see this, and I know it's a polynomial graph, what's its equation? Go back the other direction. And we figure it out with the same graphic properties. This camera out a little so I can do both at the same time here. Find an equation. This is the last problem. I forgot its number. It's hard to tell from the graph, but let's find an approximate equation is the idea. So it says find a possible equation for this graph. And it comes down steeply, goes up like this, crosses the x-axis at about -16, it looks like. Wiggles across and flattens out here and then steeps up over here, but it crosses around x equals 2. And it looks like that. Here's y equals, they call it f of x or p of x. P of x. Polynomial, I guess. How about that? Oh, and it crosses over here at -2. So what's a possible equation? Well, we look at it and say, what are its zeros immediately from the graph? What are all of its zeros? Assuming that graph is real accurate. They are
2, -16.
Yeah, the x-intercepts. -2 and 2. I know actually more than that. Actually, both of these are odd multiplicity because it crosses the axis. Right? Odd multiplicity, since unlike here, it doesn't, when it's even multiplicity, it bounces off. P of x crosses. So they can't be multiplicity 2, but they could be higher multiplicity. What do you see as a difference between these two here? This is a tricky one. This is the last one. That's why I did this one here. This one crosses straight. This one flattens out. When it flattens out, it's odd multiplicity greater than 1. multiplicity one, it will go, it won't flatten out as it goes across. It'll go across at an angle to the axis, but it'll go across tangent to the axis. And this I didn't write previously, but when it's tangent to the x-axis, it means its multiplicity is greater than 1. I don't know that it spells this out in the book real well, but they still seem to expect you to figure it out in this problem. So this is odd multiplicity because it crosses, but it's multiplicity greater than 1 because it flattens to become tangent to the x-axis. So it must be multiplicity 3 or 5 or 7 or something. So I'm going to guess that it actually has multiplicity 3. Could be another odd power higher, but I'm going to guess that one. And this is sort of a guessing game here because you just got a rough graph, right? But this one is multiplicity 1 because it crosses at an angle, not tangent to the x-axis. Not tangent to x-axis. It says if it crosses, it says multiplicity equals 1. So this one has multiplicity 1, -2. Crosses at an angle, multiplicity 3 or 5 or 7 or something like that over here. Well, wait a minute. Now, assuming it's multiplicity 1, multiplicity 3, and these are all of the zeros, all of real zeros at least, then here's a polynomial p of x that fits that. It's a4 times x minus x1 times x minus x2 times x minus x3 times x minus x4 by equation 1 with assuming n equals 4 from our guess here. So n equals 4 to accommodate multiplicity 3 and multiplicity 1. 1 plus 3. So it looks like that, and it's a4, the lead coefficient, times x plus 2, that's minus a -2, x minus 2, x minus 2, x minus 2. And what should a4 be? This is the tricky part of the last problems. What should a4 be? Here's a nice way they calculate it. Put in x equals 0 to see. P of 0 is equal to what from the graph? Oh, it's minus 16. Right? It crosses at 16. If I put in x equals 0, we call this the y-intercept is minus 16. Y-intercept is always p at 0. Plug in 0 to get the y-intercept. I remember plugging x equals 0 to get the y-intercept, y equals 0 to get the x-intercept. So the y-intercept is negative 16. There's my brain has again. And then you plug in x equals 0 on this side, and you get a4 times 0 plus 2, 0 plus minus 2, 0 plus minus 2, 0 plus minus 2. Let's see, minus 8 minus 16. So minus 16 equals a4 times minus 16. What should a4 be? Apparently a4 equals 1. So from this y-intercept, we can figure out what the lead coefficient is. It ought to be 1 on this polynomial. And now we've got it because we know it looks like this. And we know that a4 equals 1. Where does mean therefore p of x must be 1 times x plus 2, x minus 2, x minus 2, x minus 2, and write it as x minus 2 cubed. There's how it factors, like that. On the answer, I don't remember. Maybe I should look and see what it says for the solution here. Yeah, they just left it in factored form. Well, let's see what it says down here. Yeah, there it is. So here's the answer they're expecting is exactly that form. You type in x plus 2, you leave off the 1 in front. Times x minus 2 cubed is what they're saying should be the correct answer. So try typing that in the answer for the last blank. You probably got a different polynomial, but it'll be the same kind of concept. I think that's all on polynomials. How about that? One last topic this semester, right? And I should have, I'm sorry, I didn't move the camera over here at the end. Let me reiterate that for the people who are online. Several of you here. this over more. I don't know how much of this you saw. Part of it was missing. So we found the zeros from where it crosses the x-axis. Where it's tangent, we said that the zero's multiplicity. Where it crosses, the multiplicity is odd, and where it's flat crosses, it's multiplicity odd greater than 1. So we guessed this for the zeros. If these are the zeros, then it factors as x minus the first zero plus x, or times x minus the second, x minus the third, x minus the fourth. And then times some lead coefficient, which we can figure from the y-intercept. If the crosses at minus 16, that's p of 0, right? When you put in x equals 0, you get y equals minus 16. And you put in 0 on the right-hand side, you got 2 times 2, minus 2 times minus 2 times minus 2 here times a4 equals minus 16, tells you that a4 is 1. And you say this is the answer. That's the polynomial we think is being plotted there. You can run it in your calculator and see if it looks right. But I think these are supposed to be intuitive, so it's not going to be. They're not going to be one of these in multiplicity 5. None of these are going to be more than multiplicity 4 ever. That's going to do with fourth degree. But oh, it's too complicated for nothing. All right, so the last topic now, back here, is 7.4 on rational functions. It's going to open. Go. These polynomials, like I said, are used extensively in mathematical models because they're easy to work with, especially in calculus. Using calculus with them. But another function that has some useful properties is a rational function. You've seen these also, although they're less important. Is a function f of x, p of x over q of x, where p of x and q of x are polynomials. So a quotient of polynomials is a rational function. And sometimes they can have a common factor. If there's a common factor, we assume you cancel it out ahead of time. So if these two have any common factors, cancel them and then deal with them. So we'll say rational function is actually this, where these are polynomials with no common factors, you would have canceled them. That's all a rational function is. We call it equation 2 or something. These have very interesting results because one, what are the x-intercepts of these? Folks, I want to do a similar analysis to what I did with polynomials today. X-intercepts are important. People are always going to look there and see if it's touching the x-axis in the right spot, right? Or what? It's actually an easy answer if you think for a second. It's late in the period. I know it's hard at this point. How can I find where this function is equal to 0, right? A 0 of a function is where the function is equal to 0. When is this equal to 0? If and only if the numerator is 0, right? You want a quotient to be 0. The numerator has to be 0. Because you've removed the common zeros of these, the denominator can't be 0 at the same time, so you can't get 0 over 0. The zeros of this is precisely where the numerator is 0. Right? Oh, they're the zeros of this polynomial, right? Engineers use these, have these pole zero plots, these rational functions, and the poles are where the bottom one is equal to 0, and the zeros are where the top one's equal to 0. So the poles and zeros of rational functions are actually very important in electronics engineering. These are the zeros of p of x. So we can plot the x-intercepts of these very nicely, but it does something else. You can have vertical asymptotes where p of x, q of x equals 0. I'm going to call that a pole. There is a vertical asymptote. You can kind of think why, right? Why would you get a vertical asymptote where q of x is equal to 0? Well, for one thing, it's undefined. You can't divide by 0, right? But if you're real close to a point where q of x is 0, then this is really small, right? And this one is presumably not small because we don't have any common factors. This one is not equal to zero where this one is. So this one is some number that's not close to zero. And this one is some number that's really close to zero. It's a giant quotient, plus or minus, right? So you have a number that's not close to zero over a real tiny number, it gives you a real big quotient. Undefined. So f of x is actually undefined at the zeros of q of x, where q of x equals 0, and large in absolute value, very positive or negative. Near these places, you've got a number that's not close to 0 over a number that is close to 0. So you got a vertical asymptote. Vertical asymptote is a line that's approached by the function. So it's a vertical line approached by the function. You got a vertical line, x equals x k, where xk is a number, a 0 of q of x. Whatever number xk gives a 0 of q of x, that polynomial gives you x equals that number as a vertical asymptote. And then finally, there's one more thing it does. If I'm going to use this notation, deg of p of x, what do you think that means? All right, deg of p of x. Yes. Common notation, so we'll introduce it now. It's like degree, right? If the degree of this polynomial, like if its fourth power is the highest power, then its degree is 4. If the degree of p of x is less than the degree of q of x, what do you think is going to happen for this when x gets large or x gets real negative? Degree of this one is smaller than this one. Like if this is third power and this is fourth power, then the denominator is going to become much bigger than the numerator, plus or minus, which means the quotient will become real small and the quotient will approach 0. And if the quotient is approaching 0, the graph looks like this. It's approaching the horizontal asymptote y equals 0. So if the degree of p of x is less than that of q of x, then y equals 0, that horizontal line, is a horizontal asymptote. Approached like this, or it could be approached from the negative side. Maybe it approaches like this. Y equals 0 is a horizontal asymptote on both sides. It might go positive on one side, negative on the other, or positive on both sides, or negative on both sides. It doesn't matter. But it's a horizontal asymptote on both sides. Actually, this is a vertical asymptote on both sides. And then finally, if the degrees are equal, degree of x, p of x equals the degree of q of x, and we'll have to argue this later when we have a little better example. You can still get a horizontal asymptote. Then y equals the quotient of leading coefficients of the two polynomials is a horizontal asymptote. I'll abbreviate coefficients as coefs. Those are the only asymptotes. If the degree of p of x is greater, there's just no asymptote, no horizontal or vertical asymptote. You have a skew asymptote, like a slanted one. We won't do that. Those are for calculus and that kind of thing. The reason being that we don't go into more detail here is we haven't got the mathematics to do it. What is an asymptote? We said it's approached. What does that mean? We haven't made that rigorous. You make it rigorous in calculus, unfortunately. So we can't rigorously define asymptotes. We can only say it gets closer and closer. You know, we know what that means intuitively, but we can't prove anything because we don't have the rigorous definition. But here's how you plot rational functions is you can plot their zeros. That's their x-intercepts. You can plot their vertical and horizontal asymptotes, and then you can plot some points on your calculator and see what it looks like. And you get a pretty good graph of these rational functions, which are not as important as polynomial, but pretty important. And when you have something you want to model is blowing up, to infinity, then the rational function is what you need. And there are models that you need that for. So here's some of these problems. I just plug in the points. Here's one of them I gave you on your practice test. This is number 3. This is kind of a fun one, I think, because it's one that everybody experiences. A train whistle sounds higher when the train's approaching. You've ever seen a train coming? It's going, and it changes its frequency of note, changes the pitch, they say on here. Pitch is more complicated than that, but all right, so it changes the frequency of the approaching train. Suppose a train whistle has a frequency of 440 hertz. AC. This means cycles per second. The air vibrates in 440 times per second. Is that amazing? Yours can detect that. This is the A note below middle C. So it's a middle A, I guess you can call it. I don't know. Middle C is right in the middle of the piano, right? If you took piano lessons. And then A note is just 2 notes below that, 2 white keys below that. Then you note the note you will hear. The note of an approaching train with velocity v is P of v equals 440 times 332 over 332 minus v. Where v is in meters per second. What do you think this 332 is? It's the speed of sound in normal air, about 332 feet. So if the train approaches at 332 meters per second, then it's going Mach 1, it's going the speed of sound. And then you get a division by 0, it makes a shock wave instead of a pitch. And so you get the sonic boom kind of thing, right? Shock wave. So that's why this asymptote actually is significant. Is where if V reaches 332 meters per second, you get a sonic boom instead of a pitch of a whistle. Your whistle will sound like a big boom as it goes by. All right. So then they say, fill in the table. Too much time on this. To plot points. Well, you just run it on your calculator. It's easier, but you have to fill in the points for homework just to kind of have a feel what's going on. Here's V and here's P of V, and all you're doing is plotting points on this rational function, right? Instead of this is P of V here. I wrote that poorly. All right, this function of V instead of X is a polynomial, just a number, right? This is a 0th degree. A number is a 0 degree polynomial. And this one, AV plus B, is a 1st degree polynomial. So degree 0 or degree 1. It's a rational function, a polynomial divided by a polynomial. All right? Degree 0 over degree 1, a very simple case. So I look for on this horizontal and vertical asymptotes, zeros of the function. What are the zeros? There aren't any. The numerator is never equal to 0, so I'll just put none. Or they may say DNA on there. You're going to have to see what the instructions say. Anyway, so for plotting, I'll say there are no zeros. No places where the pitch is 0 because the numerator can't be 0. What are the asymptotes, vertical asymptotes? they're the zeros of the denominator, right? Where the denominator is zero. So it's 332 minus v equals 0, or equivalently, v equals 332 is the vertical asymptote. All right? Instead of x, I wish they would put this as x, but v for velocity is kind of nice too. All right, so there's one vertical asymptote. Is there a horizontal asymptote? It's the horizontal asymptote. If the degree is the same, then it's the quotient of leading coefficients, we said. I raised it, unfortunately, it's a hard question. If the degree of the top is lower, this is degree 0, this is degree 1, so it is, then the horizontal asymptote is y equals 0. So the degree of the top, p of x, is 0. Degree of the denominator, q of x, is 1. Degree of p of x is less than the degree of q of x. So you have horizontal asymptote y equals 0. So I have a horizontal asymptote y equals 0, a vertical asymptote v equals 332, and I plot a bunch of points here. Like I say, suppose the thing is going at 100 meters per second towards us. What's p of v? Well, I just plug it in. 440 times 332 over 332 minus 100, minus a negative 100. This is actually when it's traveling. It's not approaching here, but I guess it's departing technically because the pitch is going to be lower. Going velocity negative, so it's going backwards behind. Anyway, let's see, 440. Just calculate 440. This is what you have to do in your homework. So it's 332 divided by 432 gives me 338 hertz cycles per second. So this is a lower note, right? This is a higher pitch. This is a lower pitch. It's only about 3/4 the pitch of this one. So it's making a lower note as it is past you and going back behind. Now we can make it, suppose the train is only traveling at minus 50 meters per second. Then I've got 440 times 332 over 332 minus a minus 50. So it's 440 times 332 divided by 382. Now I get the 382 for this hertz for this one. And so you fill in the table with these kind of numbers. And then you can plot, you can make a sketch based on these vertical asymptotes, or this vertical asymptote, this horizontal asymptote, that there's got no zeros, it never crosses, and you plot a few points, and you can do it on your calculator. Sketch and use calculator. Put it up here, I guess. Here's V, plotted at minus 50, minus 100. Put out here, at minus 332, there's a vertical asymptote. And if I plot it at minus 50, I get 338. 382. If I plot it at minus 100, I get 338. I didn't divide this. Divide by 432. Yeah, okay. That's 382. Oh, I'm sorry. When it's plus 332, V equals plus 332. Good. Right, so the denominator is 0. And so what you have is these kind of points: 382, 338. You can plot your curve through here towards the asymptote. It should be going up, approaching this vertical line, and heading down towards this horizontal asymptote. Y equals 0 is the horizontal asymptote. Y equals V equals 3. Oh, it's P. So P equals 0 is a horizontal asymptote. Y equals P equals 0 is the P axis. And then V equals 332 is a vertical asymptote, so approaches this one here, approaches this one here, and it looks like that. You can put a couple points in there. How about that? Can you sketch those for the final exam, hopefully? And then you can also plot it on the other side. In fact, if you plot the other side and allow V to be positive because it's going the other direction, what you find out is here's the vertical asymptote 332. It goes up like this. And this function over here. I think this thing actually looks like this. We're not interested in it. But you can't actually plot it on the other side. It has supposed to asymptotes on both sides, so it actually looks like this. You've got quite a few more points to see. All right, so everybody got it for next time. Do the infinities on 7.2 and 7.4. Look at the final exam practice problems and bring questions, right? Thank you for a great semester. Oh, then, yeah, your extra credit, leave that today or next time. I need it this week. If you want to make a copy of it before you turn it in, that's what I do. Thank you. Yeah, sure, yeah.